Good evening all. Welcome to the week 8 of live session for computational fluid dynamics using finite volume method. Just give me a second. Get started. Before getting started with this week's session, so there were a couple of things that were kind of unanswered in the last session. First one was on quadratic cells. So we were discussing in the last week. So when we have say grid with, so this is my P cell, this is my E cell, and this is my east cell. So we kind of wrote, so this is my east face, dt dx on the east face as a function of P cell, E cell and east cell. So if you consider this as our origin, like a local origin, and this is say delta 2, say consider we have a non-uniform mesh, this is delta 1 and this is delta 3. So in the last week when we were trying, we started out with the assumption that it is a uniform grid, but let us consider a general case when we have a non-uniform grid. So how do we go about it? So we just take a Taylor series expansion around east face. For Tp, it will be T little e towards west, so minus delta 1 dt dx on the east face plus delta 1 square by 2 d square t dx square d square on the east face, and so on. And similarly for the cell center towards east, T capital E will be T little e plus delta 2 factorial d square t by dx square on the east face. And then similarly for T double east, we have T little e plus delta 3 So now if we compare LHS with RHS, so we compare each of the coefficients. So if we compare the coefficients for T little e, on the LHS we don't have anything. On the RHS we have A plus B plus C. Similarly we compare coefficients for dt dx. LHS it is 1. On the RHS we have minus delta 1A plus delta 2B plus delta 3C. And similarly we compare the coefficients for T square T dx square. LHS we have 0. On the RHS we have delta 1 square A by 2 plus delta 2 square B by 2 plus delta 3 square C by 2. So now we have 3 equations and 3 unknowns. If we solve them, we will get the values of A, B, C. So in the interest of time, I have just a little algebraic manipulation. So this is for the linear case, we did it in the last week. Now when we have a quadratic profile assumption and we get these 3 equations, and if we just do some rearrangement and solve for them, so these are the equations we will end up with. So these are the coefficients A, B and C that we will be ending up. So in the last week when we were discussing, we assumed it to be a uniform grid. So in the case of a uniform grid, we will have delta 1 equal to delta 2. So if we substitute delta 1 equal to delta 2, the coefficient C will essentially be 0. So that's what we arrived at in the last week. So for a uniform mesh, for a uniform grid, both the case of considering linear or quadratic profiles is essentially giving you the same expression for the gradient on the east face. Now alternatively you can also think of it in a different way. Say, so there was a question last week where someone asked why are we calling it a quadratic assumption when we are essentially taking a linear combination of the cell centroids. So the rationale behind that is, so if this is your P cell, so what we are doing here, between P and E we are assuming a linear profile. So T, we are assuming it as A plus Bx. So if it of this particular form, then we have two unknowns A and B. To determine these unknowns, we are just giving the conditions at x equal to, say, this is delta 1 and delta 2. At x equal to minus delta 1, we have t equals to Tp, and x equal to delta 2, we have t equals T capital E. So if we solve these two equations, then we will get the values of A and B. So delta 1 will be Tp and will be T east. From this you will get B equals T east minus Tp by delta 1 plus delta 2. So essentially dt dx on the east face is B. So this is a case for a linear assumption. So what we mean by quadratic assumption is we have P and E, but instead of assuming a linear profile, we are now assuming a quadratic profile, A plus Bx plus Cx square. And if this is considered as our origin, and we will follow the same notation. So this is delta 1, this is delta 2, and then we have east which is at delta 3. So for that particular case, our conditions will be at x equal to minus delta 1, we have t equals Tp, x equal to delta 2 is on the east center, we get t equal to T capital E, and x equal to delta 3 will give you t equal to T double E. So now here again, if you substitute this, you will get three equations. So these are the three equations you will get, and then our objective is to get the value of dt dx at x equal to 0, that is on the east face. So that is equal to the value of this particular coefficient. So if I just solve these equations, I will get the value of P as something like this, in terms of delta 1, 2 and 3. Now for the case of a uniform grid, when you have delta 1 equal to delta 2 as delta x by 2 and delta 3 is delta x, and if I just substitute that, then B will essentially turn out to be the one we got for the linear profile. So for a uniform grid, it doesn't make any difference between a quadratic or a uniform grid. So I think this is clear. And before actually continuing with this week's session, so there was another question in the last week where I've kind of we were solving it. So just to give you a recap, so we were solving this particular question number 5, where we have a diffusion equation in spherical coordinate system, and the boundary conditions are Neumann conditions. So we discretized in one way, and like we discretized the faces first, and then whatever are the cell centroids, we label them as our nodes, say 0, 1, 2, whatever nodes we have, and this is r equal to 0 and this is r equal to capital R. So when we were discussing, we have one of the question asks you to find the value of concentration at r equal to capital R, but as we know, like we only store the cell centroid values, so we know only C0 to C4, or in general say this is my n10, this is my n minus 1. So I just know C0 to C0, C1, so on till Cn, but I don't know the value at C at r equal to R. So how did we solve that in the last week? So my question is to find the value at r equals to R. but I know only these values, C0, C1 to Cn. I don't know this value. So one approach we started out with is just take the boundary condition del C del R. This is the boundary condition that is given in the question. So you just approximate it as del C del R as C at on the surface. I'm just calling it Cs. So if this is notated by C surface minus Cn by delta R by 2. So we are essentially taking this as the n cell. This is my surface Cs. This is Cn, and this is, if it is a uniform grid, so this is delta R by 2. This is just the half cell. So this we are assuming as J, and from this if you solve, you will get the expression for Cs. This is one approach we discussed in the last week. Now the question is, we are doing this approximation essentially because we formulated the problem in a way the phase falls on the boundary. But what if we consider the cell centroids initially? So we split the domain first on the cell centroids and then we split the phases, something like this. So this is my 0, 1 and so on. This is my nth cell. If I do it in this particular fashion, if I solve all the discrete equations, I would directly get the value of Cn. So then Cn will be equal to Cs. So the question that we stopped at in the last week is essentially why are we following this approach and not this approach? Any guesses or any idea that you might have? So if you recollect, the equations we get are something of this sort, where each of your coefficients, each of these coefficients will have an R square term. If you see an R square term here, so each of your coefficients will have an R square term. So what happens is, when you write equations here, for this particular half cell, you will have something like R0 square times C0 equals something on the right hand side, but like it will be some sigma A and B, C and B plus B kind of form. The problem here is this is our del t. So in spherical coordinate, your R0 is essentially equal to 0. So even though you have C0 to Cn as your unknowns, now because of this coefficient being equal to 0, you will essentially not able to find the value of C0 at t plus delta t. I hope you got that. So you essentially have n equations, but then you have n plus 1 unknowns. You will not be able to find this value. This is not a problem here because here R0 is not equal to 0. So R0 is essentially delta R by 2. So you have a finite value of R0 for C0, so that you will be able to find that value of C0. But in the second case, when you consider the node on the left hand side, you will not be able to do that way. Alternatively, you can use a non-uniform grid and do other stuff which we will not discuss. But the idea is fairly simple, like it's straightforward. You can consider something like this. Why do we consider non-uniform grid? Or like, is there an advantage with non-uniform grid compared to a uniform one? Yeah, you will capture the gradient terms much more accurate using some finer mesh in the boundaries. So you just want to do accuracy only where it is needed, and usually for the problem that we have stated in spherical coordinates, near the surface your gradients are much higher, so you need to have a much finer mesh near the surface so that you will be able to capture them. The equations are all will be similar, so the equations are same as this, the coefficients will be the same. The only difference you will be facing is previously we just considered the delta R to be constant, but now here you will have each cell will have a different value of delta R. You just need to correspondingly, like it's just a matter of bookkeeping. You just need to take care of what delta R you are using. Other than that, all the equations remain the same as we have discussed in the last week. So now we'll get started with this week. So this week essentially discuss about unstructured meshes on steady diffusion equations. So the problem we'll be looking at is this. So we have a triangular domain ABC, and the cells are like 0, 1, 2, 3. These are the cells given by their cell centroids. So if this is an equilateral triangle, yeah, the first question is quite straightforward. So do you think the mesh is orthogonal or not? If all of these are equilateral triangles, each one 0, 1, 2, 3, all are equilateral triangles, so if all the triangles are equilateral, so first question is essentially whether the mesh is orthogonal or not. So how do we say it is an orthogonal or not? Shall we take any of these two cells? Say we consider ADEF. So the cell centroid is 1 and the cell centroid is 0. So along the norm, you take the face normal. So this is my area vector, and then you consider the line joining the centroid, cell centroids of both the cells. So say this is R bar. So you consider the cell as orthogonal if AF bar is parallel to R bar. So each of the face normal vector, if it is parallel to the line joining the cell centroids, then those particular cells are considered orthogonal. So when you are having an equilateral triangles like this particular case, if you happen to see, it's always orthogonal to that particular face. So if this is the face, the cell centroids will be perpendicular to it, or like if you recollect from your geometry, a line passing through the cell centroid in an equilateral triangle will be a perpendicular bisector of the opposite side. So it so happens that this particular configuration shown here is orthogonal. The next question is essentially you have to discretize your governing equations for all the cells, and then we need to solve them and estimate the temperature profile along the line CD. So in the interest of time, I am just going through the solved equations since it takes a little bit of time. So the governing equation is a steady state equation. So we have del square t plus 1 minus t equals to 0, and the boundary condition is a convective condition where you have h equal to 1 and t infinity. I am assuming it to be 0, or it's essentially we are saying we have subtracted the ambient temperature throughout the domain. So we can assume t infinity to be 0. So we will take cell by cell. So if we apply the cell balance equation, it comes out to be something like this, where you have the fluxes over each and every phase equals to plus the source term should be equal to 0. So that is this equation. So you have del T dot A, that is the flux along phase AD, plus DF plus AF, plus you have a source term of 1 minus T. Now the T we have to consider here is the cell centroid value 1 minus T1 into the volume of the domain is here in particular case area of the triangle AFT equal to 0. So now we need to calculate fluxes on each of the face. So when you consider side AD, so the flux on face AD is essentially, it is a boundary cell. So you write it in the form of TB minus T1 by this particular distance that you can get from the geometry into the area. Area is the particular length of the line AD here. So essentially we are considering a unit width along the other direction. So if this is my x and this is my y, so we are assuming that along the z direction it is of unit width. So here the area of AD means the length of the side AD, that is half, since it's an equilateral triangle. Now for a convective condition, we don't know the value of TB. TB is unknown, so how do we solve it? Is we just use so like before, so this is your self-centroid value, this is your boundary value, this is your T infinity. So you kind of assume a resistor kind of thing, where here you have this resistance will be delta x by k or delta x by 2, since it is only half cell, and then this will be 1 by h. So T1 minus TB delta x over 2k is TB minus T infinite by 1 by h. So this essentially gives you T1 minus T infinite by delta x by 2k plus 1 by h. So you can solve this. This is essentially equal to this. So that is the step here I have taken. So TB minus T1 by this is that particular resistance equals to T infinity, we are assuming 0, minus TB by this. So if you just add these equations, so you will end up with this. So the total flux will be given in terms of the gradient term and the area. Now consider the side AF. Now if you see this triangular domain, this boundary condition and this boundary condition are similar. So you don't have to solve separately for AF. By symmetry you can say like AD is equal to AF. So it will be the same flux on both AD and AF. That is straightforward. Now for the side DF is where we get focus on. So if you have to focus on this, in this particular case, this is your area vector and this is the line joining the centers. Both are parallel, so it is orthogonal. So this is as per the notation we are following in the lecture. So this is E epsilon and this is my E eta hat. So the gradient along E epsilon direction will be T0 minus T1. Along this direction is T0 minus T1 by this particular length, that is delta epsilon. So I've just taken the coordinates of cell centroids. So you know these cell centroids. This is something like 0.75 and then half of this, root 3 by 2, sorry, root 3 by 4. So now you know the coordinates of all the vertices, so you can essentially get the cell centroid values. So for 1 it is a plus d plus f by 2, f by 3, and 0 it is d plus e plus f by 3. Similarly you can get all the cell centroids. So these are those cell centroids. So you can calculate the distance between them. So the flux along this particular is d, sorry, so this is df. Along df is given by T0 minus T1 by delta epsilon is 0.206. So I just substitute the value, so you'll get the value of the flux. Now we have all the fluxes, just we need to sum them up. So this is along AD, this is df, this is AF, plus you have a source term here 1 minus T1 times you just calculate the area of equilateral triangle, root 3 by 4 times a square. So that will essentially solve the equation. So you'll just get one equation for cell 1, and if you see all the cells here, so all the cells are essentially similar. So cell 1, cell 2, cell 3 are identical since the boundary conditions are same everywhere. So if you get the equation for cell 1, you don't need to solve for 2 and 3. So they have the similar equations. The only cell that is different is cell 0. So in this particular problem, by symmetry, our problem got reduced to essentially solving only this system, only ADEF. If you were to solve that particular system, it's like if you get equations for that particular system, you can solve for the entire problem. So the next different cell is cell 0. So for cell 0, it's again the similar. So you just take the gradients, fluxes along phase DF, EF and ED, and then plus the source term. That is the balance. Now we know by symmetry, DF, EF and DE are all same. So you just take along only one phase. So how do we calculate along phase DF? That is exactly what we have done previously. So we already calculated the flux on the phase DF in the previous calculation when we are doing for cell 1. So we just use it. The only difference is when we were doing in this particular case, the direction, the flux direction is along the outward normal to the phase DF. So it is pointing from 1 to 0. Now when we are on cell 0, this is my DF phase, and in this particular case my area vector will be pointing in this direction, and this is essentially my E epsilon, this is E eta hat. So here the flux will be pointing along the opposite direction to the one we have considered previously. So everything will be same, just that with a minus. So you have T1 minus T0 by that particular value that we got previously. So if you solve this, substitute this equation in this, so you will come up with a new equation in terms of cell-centered values for 0 and 1. So you have two equations and two unknowns, so it should be fairly straightforward to solve them. The next question is essentially to get the value of temperature profile along the line CD. So we know only the values of T1, T0, and then the boundary value. TD is the boundary value. So we have the equation in terms of when we solve for the so from here we can get the value of TB is the boundary temperature in terms of T1. So you can actually determine that value, and if you just make a plot of it, you get something like this. So it's essentially you have the profile has some maximum value at the center and then just comes off to the boundary. So unlike like this is quite straightforward like the ones we have solved previously. The only difference is previously when we are solving in 2D problems, we are having 3 neighbors, but in this particular problem we just previously we are having 4 neighbors. We have east, west, north and south, but here we don't have something like that. So we just have to consider the neighbors appropriately. So for the first cell we just have one neighbor, like for 1, 2, 3 we just have one neighbor, and for the 0 cell we have 3 neighbors. So we need to appropriately take them into account and solve our equations. The second thing we have used here is symmetry of the problem. Just by using the symmetry of the problem, we are able to reduce the number of. So here we have 4 cells. So ideally we should be getting 4 different equations, and then we should be solving for 4 unknowns. Just by using the symmetry, we reduced it to 2 equations and 2 unknowns. Yeah, I hope this is clear. Or are there any questions? Did I go too fast?
It is clear.
It is clear. Okay. So now the second question is essentially very same. It's the same domain. The only difference is here instead of considering equilateral triangles, we just consider a square plus, like we consider 1, 2, 3 are triangles, and then there is a square in between. So just from the figure, it is clear that your A is in this direction, but your cell centroids is in a different direction. So this is actually a non-orthogonal mesh. So how do we go ahead for solving this? So like previously when we have seen in all the, even in the course we were discussing, so it is based on something like nodes, but here we follow slightly different one. previously when we were solving, we were taking cell by cell. So we'll essentially solve for cell 0 and then 1, 2, and then we will get 4 equations, and then from there we will solve for all the 4 unknowns and we will get the equations. But now if we use the fact that flux on phase GD is essentially, say when we are calculating on cell 1 is equal to flux on GD when you are calculating on cell 0 with a minus. So like whatever is coming out of cell 1 along phase CD is equal to the whatever is coming inside cell 0 along the same phase. So first step we do here is calculate the fluxes on each and every phase. Once we get all the fluxes on all the phases, then we write the cell balance equations. That could be the way if you are actually implementing in the code. Instead of doing it like if you go cell by cell, then each time you are evaluating each phase value, so you are actually doing it twice. So to prevent that, you can first calculate the fluxes on each phase and then go ahead and solve them for and then frame your equations and then solve them. So the governing equation and the boundary conditions are very same. So now if we start with cell 1, so okay, before going there, so let us see, so can we exploit any symmetry here? So do we have to solve 4 equations or can we reduce it any further? So this is the domain and the boundary conditions are same everywhere. So it is h equal to 1 and t infinity equal to 0 and the same boundary conditions everywhere. Before actually trying to solve these equations, so how many equations do you think we will be finally solving with? Like, can we exploit any symmetry and reduce the number of equations?
I think the boundary conditions for cell 1 and 2 are same.
So cell 1 and 2 are same. So how many equations will be having finally that we should be solving for? So essentially you are saying T1 equals to T2. So we write equations for T1 and T0. Out of these 4 equations, T1 is essentially equal to T2. So you are left with only 3 equations. So now we are having 3 equations and 3 unknowns. So when we consider an orthogonal mesh, like all are equilateral, we were just having 2 equations and 2 unknowns. Now the problem is quite complicated, a little bit complicated, by just that we had one more equation. So now that we know like cell 1 equal to cell 2, we will write equation only for cell 1. So the first step is essentially you identify all the vertices, coordinates of all the vertices. Once you get the coordinates of the vertices, the next step is to get the cell-centered values. So for cell 1, it is just a plus g plus d by 3, and then 0 is just it's a square, you just calculate the cell centered of the square. The next step is to write the cell balance equation. So we have flux on phase AD, BG and GA plus the source term equals 0. The source term has a volume component, here you get the area of the triangle. So now the next step is again very similar to the previous one. So you need to calculate the flux on phase AD. It is a convective boundary condition. So it goes something like same as the previous one. So we have a T1, TP and then T infinite, which is 0. So this particular thing will essentially depend on the value of K, and in this particular question we don't have the value. The thermal conductivity value is essentially 1. So this will be the delta X between this and this, and this is given as 1 by H. H is anyway 1 in this particular case. So if you use the component or dividend rule, you will just get something like this, and then the flux is essentially this gradient times your area of triangle ADG. So that will give you one flux on phase AD. Now when coming to phase AG, it's again very similar. So the only difference is it's a little geometry here. So this is your cell centroid, and then you need to find this particular distance. So this is the delta from the cell centroid to the phase AG. So to do that, I need to know this particular value of, if I know this angle alpha, you know the total angle is 60 since it's an equilateral triangle. So this is 60 minus alpha. So you know the coordinates of 1, you know the coordinates of C. So you can get the value of alpha. So you essentially know this distance, so you get the value of alpha. Once you get the value of alpha, you can actually get the value of this particular distance, since you know this angle and this particular length. You know 1a and you know this angle, so you'll be able to calculate the value of length 1b, and that will be your delta x in your boundary condition. So that will give you another flux on the face AG. So now along GD is where we need to be little bit focused. So along GD, this is our area vector. Area vector is normal to the face CD, and then E epsilon or epsilon hat is along the line joining the cell centroids. So this is our E epsilon hat, and then E eta hat is another one. So the angle between these two is essentially 0.90. So it is a non-orthogonal mesh. So you know the cell centroid values. So E epsilon hat is along, since you know the coordinates of 1 and 0, you can calculate E epsilon hat, that is essentially 0 minus 1, and then E eta hat will be along the y cap direction, z cap direction. Delta eta and delta epsilon, you can calculate those values. So now comes interesting, or the different part that is absent in non-orthogonal meshes. So if you recollect the formula, so the flux on the along face GD in terms of previously when we were calculating, so it's just the delta. So when you calculate the gradient, so previously when we were solving, so when we have del t dot a bar, so we were writing it as or usually we don't have, we have only one of them. So if you have a mesh something like this, so a cap will be along this direction, so the area vector will be I cap dy, so and this will essentially give us del t del x times dy. But now however we have area vector pointing one direction, but our gradient pointing in a different direction. So in addition to this particular term will correspond to the line joining the centroids, cell centroids, and this is the secondary gradient which will be along the E eta cap direction. So this coefficient can be calculated easily. Both these coefficients can be calculated. Since we know AF hat, AF bar, E eta hat and E epsilon hat, these coefficients can be calculated. So once you determine the coefficient values, so this is the equation you will be left with. Del t del epsilon is something that you can approximate again. So you know the cell centroid value T0 T1 by delta epsilon. So this is straightforward. So how do we know the value of del t del eta? So if you see the cell here, this is E epsilon hat and this is eta hat. Is my F bar. So del t del epsilon along the face GD is along the direction eta hat, epsilon hat. So we have T0 minus T1 by delta C. So similarly, del T by del eta along ZD can be written as, so from 0 to 1 is your delta Z, and from G to D is delta eta. Can I write this as something like T0 minus T1 by delta eta? or if you were to follow the Taylor series, so ideally it should be something like along t along eta direction, so you should have something like tg minus td by delta eta. So like following the same notation as for del t by del epsilon del c is essentially t0 minus t1 by delta c. Similarly, along the eta direction we can write it as tg minus td by delta eta. The only problem by writing in this particular way is we do not know the values of tg and td. So like we only store the values of temperature at the cell centroids and not at the vertices. So we will just leave it as it is for now, and then we will come up with an approximation for that a little later. So now we have all these equations for cell 1. If we just combine all these equations, we get something like this, equation number 12, where you have the cell centroid value, like current cell is essentially T1, that will be in terms of T0, and then you have this is your secondary gradient term, and then you have a source term. Now we have a cell 3, which is again an equilateral triangle. So cell centroid is straightforward. So this is its neighbor is cell 0, so we just consider the neighbor. For this particular case, if you join the cell centroids, it so happens that the cell centroids are perpendicular to GF, or essentially in this particular case it's an orthogonal one, so you don't have this contribution from del t del eta term. So again here all the faces face CG and CF have the same identical boundary conditions, and the equation is similar, so you have both are same. So solving for writing equation for one flux along CG and flux along CF are same, so we will take only one of them. So along CG, if we were to write, so this is the delta x for that, and it's like for a cell centroid you have 1/3 of the total length of the bisector will be your distance from the cell centroid. So if you just use that, so we get the flux along direction as Tb minus T3 by delta x over there into area is essentially CG is see the original triangle. CG is essentially half of the total length, so we have the area as 1/2. Now again, since it is a convective boundary condition, you again write the equation something like Tb minus T3 by delta x equals to Tb by 1, and that will be equal to T3 by 1 plus 1 over 4 by root 3. So this will give you a flux value. Now by symmetry, the flux along CF and CC are equal. Now along the face GF, we have E epsilon and eta, but however your area vector and E epsilon hat are along the same direction, along the y direction, and so this is an orthogonal mesh, so you don't have this secondary term. So this E epsilon dot E hat, E eta hat will be 0, so you don't have a secondary gradient. So this is the only gradient you will be having, and this is so you get a flux along that face. Now you just take a summation of that, and this is your equation. So cell 3 is straightforward. Cell 0, if you see cell 0, it has GD, EF, DE and GF. GD, the flux of GD we have already calculated when we are solving for cell 1, and since cell 2, this is for cell, this is cell 1, 2 and 3. So cell 2 is identical to cell 1, so we already know the flux along face EF. So we need to find only flux along DE and GF. So GD we already know from the previous equation. It's just that we need to put a minus before it, since the flux leaving the cell 1 is flux entering cell 0, we just need to precede it with a minus 1. So you get flux along GD. GF we also calculated previously, so we just put a minus in front of it. EF by symmetry, since cell 1 equal to cell 2, EF and DG are equal. And for DE is where you have this, and this is essentially a boundary cell, so we follow the same rule. Tb minus T0 by delta x is essentially this, so the entire one is root 3 by 4, so this will be root 3 by 8, and that is equals to Tb minus T infinity, this is just the area I am writing here. So if you solve this, you get an equation. Now if you substitute all these equations, this again will be in terms of your secondary gradient. So if we combine all the equations, we can solve this system only if we know the value of dt d eta along the phase GD. So there are two ways to get this. It's like one is a gradient based approach and the other one is a least squares method. So we will be solving using, say, the gradient based method. So the idea here is in the gradient theorem is our objective is to find del t del eta, but instead what we do is we estimate the gradient of t, and from there gradient of dot eta hat should give me del t del eta. And so if I know gradient along t for that particular phase, the gradient of temperature at that particular phase times eta hat should give me del t del eta, and similarly the gradient along that phase times Ez should give me del t del C. The question is how do we calculate this gradient? To calculate the gradient we need to know the temperatures, but the whole problem is trying to find the values of temperatures which we do not know. So temperature itself is an unknown. So without knowing this we will not be able to find the value of gradient. So the way we solve this is using something like our relaxation schemes, where, or even we have used it in, so it's in when you are doing source term linearization, where since you do not know the value of gradient t, you will assume the value of gradient t from the previous iteration as your current gradient, and then you proceed ahead. So say you are at iteration step n. At n you know all the values of temperatures, so from there you can calculate the gradient of t. Now when you are solving for the n plus 1 system, you actually need the value of gradient of t at n plus 1, but instead you will assume that it is equal to n, and with this you will approximate your del t del eta and you will solve your system. And once you solve your system you will get a new temperatures, and then you keep going on, and this loop will keep on continuing till the values of your temperature do not change from one iteration to the next iteration. So like this is very similar to the source term linearization when we have done. So even in source term linearization, so we have an SC plus, where these terms are again if they are functions of temperature, so we assume it as a function of T star, which is the temperature obtained in the previous convergence of the Gauss seidel, and then we use those temperatures to get the next values of temperatures, and once we get the values of T we update this T star from this, and then we keep on solving this till your temperature, your final solution is not changing with the iterations. So the idea is same here. So del t del eta is essentially gradient of t times your eta cat, but to get gradient of t we need to find along the phase GD, but our temperature values are stored at the cell centroids. So we are using a first order approximation where you just take the gradient as the mean value of gradients at the cell centroids. So we are just assuming it to be gradient of t0 plus gradient t of cell 1 by half. So t0 and t1 can be taken as the gradient can be taken as if you use the Green-Gauss theorem. So it goes as del phi dot dv is essentially summation of the fluxes. Again, to calculate the fluxes we need to know the temperature along the phases, which we do not know. So we are again assuming we are making another assumption here that the phase value of the temperature is equal to the mean value of the neighboring cell centroids. So like in this particular case the phase has just two centroids, so it is something of phi1 plus phi2 by 2 or phi0 plus phi1 by 2. So when we are writing for cell 0, our neighbors are D, EF, FC and GD. So we have gradient of T at 0 is essentially, we will take over the all cells. So cell 0 is this, we have D, E, F and C. So we need to take 1 by volume of 0, volume averaging of TDE times area plus EF, FG and GD. Now TDE is again T0 plus TP by 2, I am just taking an average of it. and then EF to get the value along EF. So I will just take cell 0 and cell 2, but cell 2 is essentially equal to cell 1. So I am writing as T0 plus T1 by 2, and FG will be T0 and T3 by 2, and GD will be T0 plus T1 by 2. Once I have these equations, I will substitute them, and then I get an expression for del T, gradient of T for the cell 0, and similarly for cell 1. For cell 1 we have so ADC. So AD is again, we will just take an average temperature with respect to the boundary, and DG will take T1 plus T0 by 2, and GA will be again in terms of boundary temperature. So I will get a value of gradient along for the cell 1. So once I know the gradients along cell 0 and cell 1, we will just take an average of them to get the gradient along the face. Face is GD here. So for face GD, this is EC and this is E eta. So E eta is essentially J cap. So to get del T del eta, once we calculate the value of gradient of T dot, this is my E eta hat. So that will give me by del T del eta. So once I get this expression, so now we have 4 equations, and then we need to solve the system of equations. So how do we solve it? We again use the Gauss-Seidel method. So maybe I will go through the code so that you are as you have seen, like for this simple problem, to those of you who are familiar with symbolics, not sure how many of you, so to those of you who are familiar with symbolics, you can use symbolics to derive these set of equations instead of doing hand calculations, which takes quite a little bit of time. Maybe I will share this so you can go through this later. The problem we are discussing is essentially how do you solve this set of equations. So we have 3 equations. So this is my secondary gradient term, and these are the equations for T0, T1, and I am writing T2 is essentially corresponding to T3 in the equations we derived. So here we have 2 loops. The first while loop to ensure the first while loop is for the secondary gradient term. This is for the secondary gradient, and the second while loop is essentially for the Gauss-Seidel loop. So what we do, we assume some values of temperature initially, and then we will substitute them. This is the Gauss-Seidel loop, so it's standard one. So first you update the value of T0, and then using those values of T0, you update the values of T1 and T2. Once you get all the values of T1 and T2, you just reverse it back, and then your dt d eta will get updated. So once this loop gets converged, for the initial value of T0 that you have assumed in your Gauss-Seidel, you will get a secondary gradient, and based on that secondary gradient you will get one temperature, and once you get this temperature, you update your initial guess as your final solution of your Gauss-Seidel. So your Gauss-Seidel solution will now be your estimate for your secondary gradient, and once the secondary gradient is used to calculate the next loop of Gauss-Seidel, and then this goes on till both errors is minimized, and then you will get your final temperature. So this is very similar to your source term linearization. Even there you have two loops where the inside loop is for the cos idle and the outside loop is for the temperature T star value in your in your source term. So I think this is straightforward. So if you solve these equations, this is the solution you will be getting, and then from there, once you know the values of cell centroids, you can essentially get the value of boundary temperature T0 in terms of this. So this is one approach. The next approach is using something called least squares method. So maybe one of you can briefly explain how do you go ahead in this method, in the least squares method. So my idea is to get an estimate for del t del eta. To get del t del eta, we need to know the value of gradient of t. So how do I get the value of gradient of t using least squares? So in least squares, the idea is to see that your value of phi1 or phi on the face can be written as phi1 plus grad phi dot say if this is my face centroid, so I'm just calling it with say little e, or maybe we'll put different name. So we'll call it as P P1, and similarly you can write it as P0 plus grad phi delta R P0 . So how do you go ahead with solving this equation? Or maybe we can try taking a different cell. So this is a boundary cell, so we'll just get one equation. So if you write for an interior cell, we'll get more number of equations. So we'll get 3 equations. So if you take an interior cell, so if you are writing for cell 0, this is my 1, this is my 2 and 3. So the idea here is, if you are writing equation for phi 0, it's like, since we know the value of phi 0, what we do is we write phi 0 in terms of phi 1, we can write it in terms of phi 2, we can write it in terms of phi 3. So we'll essentially get 3 equations. But however, when we are writing this, we'll make use of the fact that you have a gradient term here. since we know the cell-centered values, that is, we essentially know phi 0, phi 1, phi 2 and phi 3, and our objective is to find grad phi, where grad phi is essentially so this essentially has two unknowns, and we have three equations. So when you have two unknowns and three equations, it's so this is where you use something called so least squares method is essentially where when you have more number of equations than the unknowns, so you only just get something like your best fit that you are solving in linear regression kind of. So your equations will be something like phi 0 will be written in terms of phi 1, plus delta phi del phi del x so you know the coordinates of 1 and 0, so you can essentially get this is my delta x 0 1 and this is my delta y 0 1. Similarly, you can get for all the coordinates. So you can write these three equations in a slightly different way, where you can write it as CO1 so this is essentially 3 by 2, 2 by 1, and then this is a 3 by 1 matrix. So you can write this as so our objective is to find this matrix. So this is A times x equals to B, but unlike the normal way where you can just do an inverse, here inverse doesn't work, since it is not a A is essentially not a square matrix. So you do the pseudo inverse. So how do you go ahead with that? So if you are familiar with linear regression, in linear regression what we do is when we have something like this, so you have ax plus y equals to ax plus b, but then we have several I, so yi equals to axi plus b, so I equals say 1 to n. So we have n equations, but we just have two unknowns, A and B are the unknowns. So how is this related to this? So in this particular case, your y is essentially your RHS and your x is your and so on. So how do you solve this equation? Is we'll assume a value as sigma y minus y square, and we try to minimize this. You will find the value of A and B such that this particular value is minimized. So here that is what you do in a linear regression. So you essentially try to minimize y minus axi minus b whole square. So similarly, in our particular case, what we try to minimize is these expressions. So you have phi 0 minus phi minus del phi del x delta x 0 I minus del phi del y delta y 0 I whole square. So we try to minimize this equal to I is essentially your neighboring cells. So if you are considering for cell 1, you just have one neighbor, so you just get one equation. For cell 0, you have 3 neighbors, and 2 and 3 essentially have one neighbor each. So how do you go about solving these equations? So this I am writing it like just this is your yi minus axi minus b whole square. Okay, we have another term here, but the idea is fairly straightforward. So how do you solve this equation? So if I call this as r square, so you just write del r square by del a equals to 0 and del r square by del b equal to 0. So this gives us or maybe we'll solve for our own equation. So when I have this as my original equation, say let's say it is j. So our objective is to we'll call this as a. J equals summation phi 0 minus phi I square minus a times delta x 0 I b times delta y 0 I whole square. So del z del a equals to 0. This will essentially give you the value of a, and del z del b equal to 0. This will essentially give you the value of b. So del z del a is essentially 2 times summation of minus phi I times minus delta x 0 I equals 0. So which comes down to phi 0 minus phi I times delta x 0 I equals a times sigma 0 I square plus b times sigma x 0 I y 0 I. So this is one equation. Similarly, when you solve for del g del b equals to 0, you will end up with sigma I phi 0 minus phi I delta y 0 I equals a times 0 I delta y 0 I so this is the second equation. So if you solve these two equations, you can get the values of a and b, and those will give you corresponding values of del phi del x and del phi del y. To write it in a more simplified or condensed form, this can be written in a matrix form. So you can write it as say if you have 3 neighboring cells, times AB will essentially give you so if you call this matrix as X, so X times X transpose into AB, essentially giving you x times. This matrix is called cap phi. So x times x transpose is again a square matrix. So AB can be directly obtained as whole inverse x times phi. So phi is essentially the difference between the cell-centered values of the corresponding cell and the neighboring cells. So once you obtain the values of phi and you know the values of x, x is essentially the delta between the the cell-centered values, so you can calculate delta x between these cell-centroids. So that will essentially give you capital X matrix. So once you know this, the values of gradients can be directly calculated using this formula. And once you get the gradients, the next step is to estimate the gradient value at that particular phase. So to your secondary gradient, like we have seen, to get the value of secondary gradient, what we have to do is gradient of t dot, we need to calculate the E eta cap. So that will essentially give you the secondary gradient. So this is for a diffusion case. So I think yeah, this is clear. So now we have all the three components. So in the particular problem we have considered, we just have source term is essentially 1 minus t, which is already linear. So if we have a nonlinear source term, plus unstructured, non-orthogonal. So essentially this gives you the secondary gradient, and to solve that we need another kind of iteration to solve for the secondary gradient terms. So we will essentially have 3 loops, one loop for the source term, and inside that loop you will have another for the secondary gradient, and inside that you will have the Gauss-Seidel loop. Now if you are using any of these direct methods, this particular loop will go off, and still you will be left with the 2 other loops with respect to source term linearization and the secondary gradient terms. I think this is clear. So in the last week we were discussing on a problem where we have matrix derivatives. So are there any questions on that? So I kind of in the interest of time we kind of skip through all the steps. So is that clear, or oh, I hope I guess everyone left. Okay.
So in the last week we used Newton-Raphson, right, for solving the unstable equation.
Yeah.
Crank-Nicolson
scheme, yes.
Yeah. So why can't we use just Gauss-Seidel instead of going into these Newton-Raphson and Jacobian?
Okay. So how do you propose? So you're asking basically in the Crank-Nicolson scheme, when we are solving, we have something of this sort. So m times del c del t equals to f of c. If we have something of this sort, what we have done is but here you have so when you are trying to solve this equation, you will only know the value of c at the current time step. You do not know this particular value, right, at the next time step.
Yes.
So you are suggesting we will just assume the value of Ct and then solve using Gauss-Seidel. Like, can you just elaborate like how you will proceed to solve using Gauss-Seidel?
if we write in the format which has been discussed in the class, so in the AB field P is equal to summation of A and B form.
Okay, so you have okay, you want to write it using okay f times something plus
Yeah.
1 minus f times something. So this is at 0 and this is at 1.
So 0 terms we know them.
Yes,
actually.
we know the 0 terms. Okay, it's the other way around. So we will write the complete equation. So you have something like this. So you know all these terms. And you have a source term which will essentially have so you know this term as well. So
And also that phi 0
phi 0.
neighbors.
Yeah, phi 0 that is essentially the terms here.
Yeah, okay. So
These are
it is
essentially
like-
your known terms. You already know these things.
So it is like solving a system of equations, right?
Okay, understood. So you are essentially saying you essentially know all the values of phi 0. So we can directly solve for phi 1 using Gauss-Seidel.
Yeah.
Yeah, if we
can
pose it in
assume
this
some
form.
value.
Yeah. You will assume some initial guess and then you go ahead and
Ah.
solve this. Yes.
Yes.
Yeah.
So
Gauss-Seidel. Yeah.
It will be giving the same answer, right?
Yeah, you should get the same answer. The only difference is your Newton-Raphson will give second order convergence. So you can expect much faster convergence. Faster convergence.
Okay.
Yeah. Yeah, but then, okay, since it is a linear form, you wouldn't have much problems. Have any other questions?
Okay, so let's say, for example, we are solving a problem. So right now we know structured, also unstructured mesh, right? In unstructured, we know it can be orthogonal or non-orthogonal. So which one would be more closer to actual difference? Because second non-orthogonal involves secondary gradient and it doesn't show boundaries, right?
Doesn't show bounded, but you can make it bounded using some relaxation schemes.
Yeah. So which one will be more close to actual lessons? More close to experimental lessons?
No, that is a different one. So your basic question is which one of them will be more accurate?
Yeah, more accurate.
So accuracies again depend, like you have assumed linear profiles and all of that. So depending on your profile assumptions, all of them will be a first order or second order accurate.
Okay.
So the next problem with respect to experimental results when you want to compare. So if you have when you are using unstructured meshes, you have better control over your mesh, so you can better approximate your geometry. So if your problem is more dependent on your geometry, then using an orthogonal structured mesh, say suppose you have some aerofoil kind of shape. So when you want to use an orthogonal mesh, so you will kind of end up with these discrete things. So your geometry will be kind of different from the actual geometry you obtain using your mesh. So it's just that because if the problem is dependent more on the geometry, then an unstructured mesh will be able to do that. And then you have other cases. Say you have say circular domain or something. There you can see it very clearly. When you have a circular domain, you can use a polar grid. If instead you use a Cartesian grid, so you are essentially approximating these curves to be straight lines. So you need a much finer mesh to solve them. Or alternatively, you can use some kind of finer mesh only on the boundaries and then kind of make it coarse near the centers and all of that stuff. So your accuracy is a different thing. So it depends on how you discretize your domain.
Okay, let's say for example, instead of taking these complex geometries, let's assume that it's a rectangular domain, and I solve them using structured and unstructured.
Okay.
So in this case, which one will be more?
Yeah, your structure should be more accurate because you have introduced some approximations. But if your Gauss-Seidel is converged, then both of them should give you the same result. If after convergence, the result you get will be same for both structured and unstructured. The idea here is whenever you are using the secondary gradient in all these terms, you are just changing your weight to your final solution, but your final solution will remain unaffected.
Okay. So, like, if you use unstructured mesh, even though if we use unstructured mesh, they'll get almost the same results.
Yeah. But you need to make some, like, basically when you make it structured, you will have a different nodes, and then when you are making it unstructured, you will have a different node. So you just need to, like, it is quite complicated, right? So how do you say both are same? So you have different nodes here and here.
Okay.
So you need to make proper interpolation and get the values and compare, like, to define your metric.
Yeah, got it.
Yes, this week's assignment essentially focuses on orthogonal and orthogonal meshes, and we have discussed both the variants. So I think if there are no questions, then we can conclude maybe.
Again, the same question. So, what is the significance of boundedness? Because in unstructured, we won't be getting bounded results.
Bounded results in the sense.
In
Okay, so you are saying the Scarborough criteria is not satisfied?
No. Yeah, something like that.
Okay, I didn't actually get your question. So you are essentially asking, so when we are using unsteady, you are getting a secondary gradient term, but that is essentially going to your B term, right?
No, I'm talking about the non-orthogonal meshes.
Yeah, even in the non-orthogonal mesh, your secondary gradient term will essentially go into your B part. So
yeah, so at that time, if we compute the boundedness, if we analyze the boundedness those criteria, they will find that it will not be bounded.
no, but then your boundedness will depend on A and B and AP, right? Your secondary gradient term will not contribute to your AP term.
Yeah.
So it's like Scarborough essentially says sigma A and B by AP should be less than or equal to 1. It doesn't have the B term, right? Okay, I got your question. So you're essentially saying when you have your secondary gradient, this term can shoot up and your
this
local
B
it
term
can
has,
not
not
okay,
equal
okay.
to 0 secondary gradient.
Okay, okay. So in that case, yeah, if your solution is diverging, then you have to use your relaxation scheme.
No, in this case, so what does these mean? Like not bounded means they're not giving actual physical results, right?
Yes.
So at the end, again, we are saying that it will be giving almost same as a structure. So,
no, but then we use a relaxation scheme, right? Okay, there are two things. So even if you consider without secondary gradient, even in structured meshes, if your time step is much larger, even then your solution diverges, right? So does that mean the structured mesh is wrong? Yeah, so it's just that the way you solve it's the problem with the numerical method, nothing to do with the original problem or something.
Okay, I will explore this and I will come back if I have some questions.
Yeah, sure.
Yeah, that's it.
That's it. Okay. Okay then. Thank you all. So maybe before concluding, we can just go through the overall algorithm. When you have nonlinear source and then you have non-orthogonal mesh, so how do you do it? So first step is you guess the values. Next we need to compute the gradients. So here we have two ways. Use the gradient theorem and then compute it. So essentially it says grad phi is essentially 1 by v times sigma of Pf Af, or use the least squares method. This is done by using the assumed value of phi star at the previous step. Once you get this, next we do a while loop for all phases. What do we calculate? We calculate the value of A and B. You know this as AF dot by AF dot E zeta cap, and then we can calculate the value with respect to the particular cell, the corresponding cell, the corresponding phase as A and BF, and the neighboring cell, the next cell, it will be minus. You just need to multiply it appropriately, and secondly we need to update the secondary gradients along that particular phase, and so from there we will add that secondary gradient to the existing value of B0 term, and this has to be done for both the cells. Once you know the values of gradients and once you have compiled them into this set of equations, now you write the equations for the complete cell. So that is your AP terms. So you'll go cell by cell. And then you can write AP as sigma NB, that is all the neighboring cells, minus your source term of that particular cell. And your B0 now will have another contribution from the source term, and then you just come out of this. So now you have all the equations, you solve them using Gauss-Seidel. Now once you are in step 5, once you solve the Gauss-Seidel, you get a value of phi, and then you will make your phi star equal to the value of phi obtained from the previous step, and then you again start from 1. And then you keep on repeating this till value is converged. So how do we calculate these gradients? Say using gradient theorem. So use this approximation to get the values of gradients, and that is what we will be using later. So the algorithm is straightforward. So now that we have the algorithm, so I think now it is time we can conclude the session. Yeah. Thank you all for joining the session.